So typically at this point in a Math 112 class, students like, all right, I kind of understand these trig functions. I can memorize your unit circle if you really want me to. Sine, cosine, tangent, cosecant, secant, cotangent. I understand that those are just different combinations of the x and y coordinate on the unit circle. I have a lot of knowledge in my head now, like I've memorized a lot of stuff. But I don't understand why. Like, how useful is this? I can't see any reason why I'd want to learn all this. Finally, in 5.4, we start to get a glimpse at some of the more common uses of all the knowledge that you already have. So what we're going to do in 5.4 is we're going to kind of take what we've learned on the unit circle and we're going to expand that to deal with right triangles. What am I talking about? Okay, so here's our unit circle that we've seen before. I'm going to draw an angle in its standard position. So I'm going to kind of start down here at the origin and I'm going to measure this angle from the positive x-axis up to some arbitrary line. And that line will define this terminal point on the edge of our unit circle. To keep this all as general as possible, maybe I'll just call this angle here t. And what we've learned so far is that if we're calling this t, then the x-coordinate of this point is the cosine of t, and the y-coordinate of this point is the sine of t. And in the case that t is one of the 16 memorized values, you have numbers that correspond with the x and y coordinates. So for example, if t were, I don't know, it kind of looks like 30 degrees, pi over 6 here, maybe you would know that the cosine of 30 degrees or pi over 6 is root 3 over 2, and that the sine of 30 degrees or pi over 6 is 1/2. But I'm not claiming that t is 30 degrees. T is just some arbitrary angle here. And so all we can say is this is cosine of t and this is sine of t. Hopefully you're with me so far. What I want to do is I want to take this from circles to triangles. I want to make the point that this defines a right triangle. If I take a line and I drop it straight down here to my x-axis, I create a 90-degree angle here. And what I have drawn in green is a right triangle. Maybe I can redraw that over here just to make it a little bit easier to look at. We already know that this is t. This little symbol is telling us that this is 90 degrees. But we don't have any labels on the sides of these triangles. It'd be nice if we knew the length of each of the 3 different sides of the triangle. It turns out that we do. The fact that this is a unit circle means that the radius of this circle is 1. So the distance from the center of the circle to any point in red on the outside of this circle is exactly 1. And you might note that the hypotenuse, the side opposite the 90-degree angle here, is a radius of this circle. And therefore, the length of the hypotenuse must be exactly equal to 1. What about this side length? Well, the fact that this point has an x-coordinate of the cosine of t means that the distance from the y-axis to this point is cosine of t, the x-coordinate. And the distance from the y-axis to this point is the exact same as the distance from the origin to this point. What I'm saying is the length of this leg of the triangle is the cosine of t. And similarly, since the y-coordinate here is just the height of this point, and the height corresponds with the length of this leg of the triangle, I could say that this leg of the triangle has a length equal to the sine of t. What I'm saying is, if you're lucky enough to have a triangle whose hypotenuse is exactly 1, and you know this angle right here, then you can figure out the length of this side and the length of this side. And you're like, all right, I mean, I guess that could be kind of useful if we were lucky enough to have a triangle whose hypotenuse was exactly equal to 1. But how often do I have a triangle whose hypotenuse is exactly equal to 1? Here's some other triangle, and let's keep this angle the same. Let's call this t still and make this a right angle. But now this hypotenuse is not equal to 1. It's bigger than 1. I don't know. It looks like maybe 3 or so. To keep this as general as possible, let's call it k. It'd be nice if I could figure out this length and this length. Well, it turns out that you can. The reason you can is because this triangle in red and this triangle in green are what are called similar triangles. Similar triangles are just scaled copies of each other. What I'm saying is the 3 angles are all the exact same here as they are down here. And you're like, 3? It looks like just 2 are the same, this t and this 90 degrees. And that's true. However, the sum of the interior angles in a triangle are always equal to 180 degrees. So this angle up here is just 180 minus this 90 minus this t. Similarly, this angle up here must be 180 minus this 90 minus this t. What I'm saying are all 3 angles here are the same as the 3 angles here. So these triangles are what are called similar. This is just a larger scaled version of this triangle. And a nice property of that is if the hypotenuse is k times as long as this hypotenuse, then this side length is k times as long as this side length. What I'm saying is this side length is just k times the sine of t. And similarly, this is just k times the cosine of t for whatever number k is equal to. And maybe you can see how red is a little bit more useful than green because red is a little bit more general than green is, but it's still not the most useful form. It's still not what we're trying to take out of this video. The last step we want to do with this is notice that if you take the length of the side that is opposite this angle. So what I want to do is refer to these three sides relative to this angle. So relative to this angle, this side is opposite this angle. Note that this side never touches this angle. This angle is made up of these two sides, so I will refer to the side that doesn't touch the angle as the opposite side. And since we have a right triangle, one of the sides will always be opposite the 90-degree angle, and there's a fancy name for that as well. That's called the hypotenuse. So the only side left that needs to have a name is this guy down here, and what's typically used is the word adjacent. The adjacent side of some angle, notice this is all relative to this angle, is the side that touches that angle that is not the hypotenuse. Now that we have these names, we can come to our general conclusion that I'm hoping to get out of this video. Look what happens when we take the length of the side that we're calling opposite and divide it by the length of the hypotenuse. Well, let's see, the opposite side length, the length that is opposite this angle t, is equal to k times the sine of t. And I don't know what k is equal to, but that's okay. K is just the length of the hypotenuse. So when I divide this by the hypotenuse, I just have a k down here. And you might notice that this k, no matter what number it is, and this k are going to cancel each other out. What I'm saying is the ratio of the length of the opposite side to the length of the hypotenuse will always be equal to the sine of t. And that's true whether I'm talking about this triangle here, sine of t divided by 1, or some other triangle where the hypotenuse is not just 1. Maybe the hypotenuse is, I don't know, 10. Well, if this is 10, then this is 10 times the sine of t, but those 10s cancel out. It doesn't matter what this is when I look at the ratio. The ratio of the opposite side to the hypotenuse is always the sine of t. Similarly, when I take the length of the adjacent side to the hypotenuse, I'm taking k times the cosine of t, and dividing that by the length of the hypotenuse, which is exactly k. Those k's cancel each other out, and I'm left with just the cosine of t. The ratio of the length of the adjacent side to the hypotenuse is always equal to the cosine of t, no matter what right triangle I'm talking about. Finally, if I take the length of the opposite side and divide it by the length of the adjacent side, I would be taking this k sine of t and dividing it by this k cosine of t. The k's would cancel, and I'd be left with just the sine of t over the cosine of t. However, maybe you remember from a previous video that the ratio of the sine to the cosine has a special name. The sine is just the y-coordinate, the cosine is just the x-coordinate. If I take the y and divide it by the x, I get the tangent. What I'm saying is sine of t divided by cosine of t is just the tangent of t. So therefore, the ratio of the length of the opposite side to the length of the adjacent side is always going to be equal to the tangent of t. The fact that the ratio of these two sides gives you the sine, the ratio of these two sides gives you the cosine, and the ratio of these two sides gives you the tangent is the important piece of information that you'll need for all of 5.4. Man, how am I ever going to remember that? That's going to be really hard to remember. Well, I can tell you how people remember it. I have no idea why this sticks and why everybody does it this way, but everybody does it this way. This is one of these things that I learned way back in the day, and I was like, oh, this is just my teacher's weird little thing that we're learning at Castro Valley High School, where I went to high school. It's just our little weird thing. And then I went to college, and somebody else who was not from the same city that I was from was doing their trig work, and they referenced this same method. And I learned that it wasn't just our little thing. This is something that everybody does. They memorize this word SohCahToa. SohCahToa, what's that mean? It means nothing. It's a made-up word, but for whatever reason, everybody remembers this word. SohCahToa, SohCahToa. I typically capitalize the first, fourth, and seventh letter here to remind myself that what this is encoding are all of these ratios that I have above. The SOH in SohCahToa is telling me that the S, which stands for sine of some angle t, is equal to the length of the opposite side divided by the length of the hypotenuse, which I could abbreviate as O and H. Sine equals opposite over hypotenuse. Similarly, cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent. This weird made-up acronym is what you could think of as the title for this section, SohCahToa. SohCahToa allows you to represent the ratio of any two sides of a right triangle relative to either the sine, the cosine, or the tangent of a given angle. And that will allow us to do a lot of stuff with trig. It'll allow us to move from circles to triangles, which is where we'll spend the majority of the rest of the class. And it'll even allow us to answer the questions that we've done in 5.2 and 5.3 in what you might consider an easier way. SohCahToa will be something you'll probably really like in this class and will be really useful to you. If you were able to follow the derivation of this, that's great. But really the big takeaway is just this fact here, that anytime I have a right triangle and I have some angle in that right triangle, I can represent the ratio of any two sides of that right triangle relative to either the sine, cosine, or tangent of that angle. Rather than repeat myself for like a fourth time, maybe I'll end this video here.